So I want to welcome everybody to another Earth2Class. I did a count recently. I think we're up to 215 at this point. So as we can all say, it seemed like a good idea at the time. Anyhow, I want to welcome back Margie Turrin and Laurel Zaima, who are important parts of the Lamont educational program. Margie and Laurel, are you doing anything on campus yet?
We're on campus, period, to be in the office, but we aren't able to do programming on campus yet.
Okay, I know it's coming sometime soon.
Yeah.
Which means I have to get up an hour earlier to go buy food, get stuff set. I like this sitting quietly at home. Anyhow, today and next time, we're going to be discussing some remote sensing in polar regions. So I'm very glad to welcome back Margie and Laurel and welcome many of you. Some of you have only been here a few times. But this type of program does not require much of an introduction. So I'm going to turn it over very quickly to Margie and Laurel, and they'll take you through the program. Who's up first, Laurel?
Yeah, sure. So hi, everyone. Good to see some familiar faces, but if I don't know you, my name is Laurel Zaima. I work at Lamont as an Education and Outreach Coordinator.
Yeah, and I'm Margie. I work with Laurel at Lamont. I know quite a few of you, but not all. And we're really excited today to kind of dig into a project that we've been working with a group of Lamont scientists and actually some of the UK now, looking at using remote sensing to better understand changes that are going on. And I'm going to let Laurel start it off.
Perfect. So we do have a worksheet with a teacher answer sheet. We have the whole lesson is matched to standards with learning objectives. We can share all that information with you at the end of this program, but Margie's
has been posted on the Earth2Class website.
Perfect. So we'll post it on Earth2Class, and Margie's actually just going to pop the worksheet in the chat right now, just so you have a chance to go through each one of these activities as if you were the student. And you can just kind of see some of the questions that we're asking to have students kind of dig deeper into these different remote sensing tools. So we're using 3 different tools today that are exploring different glacier physics, glacier dynamics, and while the project is focused in Greenland, we're not just focusing on glaciers in Greenland. We're going to be comparing them to glaciers worldwide. So this is also in that learning objectives document that I mentioned earlier that we can share, but we just wanted to go over briefly these different big ideas, learning objectives, key understanding, and essential questions for today's program. So maybe just for to keep things brief, I'll just go through some of the big ideas. So overall, between these 3 different tools, we're going to be exploring how the Earth is dynamic and that it's constantly changing. And that the Earth system, you can't just look at one system without thinking about it as a part of a bigger picture. So that this system has multiple different interacting cycles and processes and feedback loops. The Earth is huge, and monitoring change requires special tools like these remote sensing features that we're going to be showing today. And that humans are a part of this Earth system, that we cannot take ourselves out of the equation, that we play a critical role. And so throughout these different tools, we are going to be answering these essential questions, and we'll kind of come back to these at the end to review, but just some things to keep in mind as we go through the program. What drives change in Earth's icy areas? How quickly do these polar regions respond to some of these changes that we're talking about? And are there certain processes that enhance ice loss or ice flow? How can we monitor Earth's changes? And then finally, how are humans a part of the Earth system? All right, so while we are talking about changes in ice dynamics, the Earth is dynamic in a bunch of different ways. So this is just a great opportunity in the chat for you to pop in some answers. We can kind of do it in a waterfall format if you've ever done something like that. So you're going to take out one example of how the Earth is dynamic, and on 3, we can all press enter and it will flow through a bunch of these different answers. If you're in the classroom, you can use different tools like Mentimeter, you can use Jamboard, but this is just a nice way to get the students' brains turning and thinking about the Earth system as a whole. Okay, so hopefully through that, you've had a chance to type in some ideas. So on 3, we'll just all click enter. All right, 1, 2, 3. Okay, volcanism, changing populations, temperature variation, weather. Awesome. It's changing constantly. Yes, so many things are changing constantly on Earth. And it's kind of fun because we're looking at different timescales too, like weather is short term, temperature can be short term and long term. Oops, sorry. My mouse is.
And tectonics is both short and long term. So yeah, there's a whole lot of different timescales on here, which is a really great point.
Thanks, Margie.
Yeah.
My mouse went crazy for a moment. Okay, awesome. Thank you, everyone. These are great. Okay, so as I mentioned, the project's really focused in Greenland, but throughout this whole activity, we are going to be talking about both polar regions as well as some glaciers elsewhere in the world. So just for spatial orientation, the globe image on the left-hand side is focusing on the Arctic, and this is Greenland. And the Greenland Ice Sheet is the second largest ice sheet in the world. And then the only other ice sheet on the world is Antarctica, so the opposite pole. This is the southern end of the world. And so while we are looking at glaciers everywhere, which is important for students to think about, that they're closer than they think, these are kind of the primary foci of this whole lesson. Okay, so just some basics to make sure that everyone has a bit of understanding about the Greenland Ice Sheet. So the Greenland Ice Sheet, this is on our right, a satellite image of Greenland. So you can very clearly see that this ice sheet covers 80% of the land mass. It's very widespreading. Only on the fringes of the Greenland subcontinent can you see some of that land area. And it covers an area of about 1.75 square kilometers. So it is massive. The ice is also so thick and heavy that it's actually pushed down a depression into the Greenland bedrock. So this image on the right, now we're looking at what the topography of the Greenland bedrock is under the ice. So if you take off that ice, what does Greenland look like? And you can see on this scale that the center of Greenland is actually depressed and pushed in, and that's due to the weight of the ice, whereas the fringes of Greenland are above sea level because they don't have that weight of as much weight of the ice or ice at all. And ice is also constantly moving and flowing. And this might be something that your students are not familiar with, because when they think of ice, they think of a solid ice cube perhaps. But when you have this much ice, the weight of the ice and the force of gravity actually causes it to flow. So this image is looking at these different ice streams and the ice velocity of these ice streams. So there's not much speed in the middle of the Greenland ice sheet, but then you can see it really increases towards the edges where these ice streams really like funnel and shoot the ice out towards the edge. So ice is constantly flowing at rates up to 12,730 meters per year. So it's I think that's a pretty incredible number. And then finally, we're looking here at ice thickness. No surprise, since we saw that depression in the bedrock, that the thickest part of the Greenland ice sheet is in the middle, and it gets thinner as we get towards the edges. And the middle is so thick, it can even reach about 3,000 meters in thickness at its center. So that's pretty incredible. No wonder the middle part of the bedrock is depressed.
So Laurel, I realize this is being recorded and I put a correction in the chat, but I wanted to make sure that it actually got into the recording. That actually that's a typo. It should say 1.7. I know when you said that loud, I know you're on a roll right now, so you probably didn't even recognize, but it should be 1.7 million square kilometers. I apologize for the typo.
Thanks, Margie. Yep, didn't even notice.
Like, that's a very small bit of ice, right?
Yeah.
That's in my driveway.
Okay, so using our first tool, maybe some of you are familiar with glacier goo, maybe some of you are not, but glacier goo is this material that you can make out of Elmer's glue and water and borax. And when you create this goo and you use it in these different activities, it actually simulates a similar flow to how ice acts in these glaciers. So it's a great way to teach students in a tactile, fun way about glacier physics. So we have the instructions on how to make glacier goo and how to run these activities that we can share, as I mentioned. But we're going to go ahead and start with our first activity that's looking at gravity. So what you would do is you would have your students on a charted piece of paper, mound up their glacier goo in a ball, put it in a circle right in the middle of their chart, and draw a circle around it. And what you're trying to observe is whether gravity plays a role on the ice movement. And so if hypothetically it is, then you would see that glacier kind of extend to the outer edges of that circle. So you can have your students think and make a hypothesis. Do you think that it will stay in the circle? Why or why not? I don't have glacier goo with me right now, but I have, let me just share my whole desktop here, on these recorded videos just to show you how it would be simulated. Drawing a circle around it. And you can see that this is on a flat surface. It's not on a decline at all, but understanding the way that gravity works is it's going to be pulling objects toward the center of the Earth, even if it's not on a decline or a slant. It's going to move from that highest to lowest point. So because the glacier goo is malleable, you can see that it has flattened and extended outside the bounds of that circle that we had drawn. So that's just our first understanding that the ice and glaciers, it moves due to the force of gravity. Okay, our next experiment, we're looking at basal friction. So basal means the base or the bottom layer of something. So when we're thinking about the basal friction of a glacier, we're looking at where the bottom of the glacier meets the bedrock. And so because there is an interaction there, there's naturally going to be some friction force between those two objects. So to simulate this, you are going to have your glacier goo mounded up in a ball, but this time it's going to be on that decline ramp. And to understand whether basal friction plays a role on this glacier, you are going to take a toothpick and you're going to stick it right through to the bottom of this glacier goo mound so it touches that map board. And you'll have your students think, and you guys can hypothesize as well right now, given basal friction, do you think the toothpick will tip downward, down the decline, or will it tip upward? And why do you think so? Does anyone want to take a guess, take a hypothesis?
Or put something in the chat
Oh, okay, yes.
if you're all muted.
I forgot to use the chat, but
Yes.
also feel free to unmute. Oh,
I'll make a guess here, Laurel. I'm going to assume that the stick will start pointing up because the bottom just kind of falls out, almost like as if somebody was working outside in their driveway and they slipped and their feet went out under them and they would fall backwards.
Oh, okay. So it's like the bottom is slipping out from under.
Yeah.
Are there any other hypotheses?
John, what is that telling you about the ice? So share with us what is that telling us about which part of the ice is moving more quickly then?
Well, the way I would think of it is that the ice on the bottom would actually move faster than the top. But what has me question myself, of course, is the title, Basal Friction Slows Ice Flow. So I could be exactly wrong.
And that's what I love about science.
I'm having an argument in my head right now.
Okay, I'm just looking in the chat. We have some people saying the toothpick will tip down, and Kathy says, I think the top is moving faster due to the larger gravitational force. Kathy, do you want to unmute and elaborate a little bit on that?
So good morning. I was thinking that more about when it was on the flat surface, that the top would have a larger gravitational potential energy than the bottom. But on the curved surface, maybe the friction is the larger force at play here.
Okay, I see now. Thank you for explaining. Okay, so great hypotheses. Let's run our experiment and see what happens. Which one is it? Okay. So you can see this is a decline ramp here. I have my start stop. And as our glacier is slowly moving down, you can see our toothpick is starting to also move down. Okay, so we have this observation. Why? Why is our toothpick tilting down? And what does that have to do with basal friction?
I would like to
Top is moving
first.
faster than the bottom.
Yeah.
Why?
I agree, and I would like to change my answer.
So James, you said the top is moving faster than the bottom, and why would that be?
Well, because friction is going to slow the ice flow on the bottom. And if you've got really irregular surface rock, definitely it's going to have more friction than going across a smooth piece of slate.
Yeah.
So
Perfect.
and when the ice sheet does make it to the sea, it's always this overhanging, it's hollow on the bottom, and the ice is extending out over the ocean because the bottom of the ice sheet is it's been held back a bit.
I think you're talking about ice shelves. So those like hanging bits that are grounded by the their grounding line, but then they're kind of floating on the edge. Yeah,
It's a little bit of a different process. So I just want to make sure that we clarify that it is a little different once it hits the water. And we can go back to that later at the end if you want.
we actually have an activity that talks about ice shelves through the Bergie Bits series. We're not going to be talking about it today, but in that full packet, there's a full explanation of how you can simulate the ice shelf function for a glacier with your students. Great. And so one minor thing that I just wanted to mention was that I had you all really talk through the process of why these things are happening. And I think that would be important for your students to bring it full circle as well. Okay, our last, oh, perfect. So this is just an example of how things are flowing and where the friction is. But James, you said it so perfectly. Great. And our last activity for Bergie Bits is looking at channel friction and how that affects flow. So what you'd be doing is you're keeping that map board on that decline slant. You're going to be putting, creating anything to simulate a channel. So anywhere that's going from a bigger width to a more narrow, tinfoil works great. So I have that here. You're kind of going to ball up your glacier goo and put it in the middle and draw a line across it. And what you're going to hypothesize is whether you think this line is kind of going to dip and create a smiley face, or is it going to create a frowny face, and why? What mechanisms are at play here? So does anyone want to make a hypothesis for this one?
Well, now you have
Go
friction on the
slide.
sides as well. So that should slow down the sides and the center keeps moving.
Yeah.
Mm-hmm.
Therefore
A
giving
big
you a
smiley
smiley
face.
face.
Perfect. Great.
We're all optimists here.
I heard two smiley face hypotheses and perfect explanation about where the friction, and where that friction is occurring. So let's run our last video here. And here we go, flowing right into that smiley face. We're happy glaciers. So this is great. You kind of explained it in your hypotheses that you have friction, you have that basal friction, but now you also have friction that is on the channels. That's going to be slowing down the movement of the glaciers on the edges, whereas the middle can move faster. And in real life, you can see these glaciers, just the way they look in real time. You can see that force playing a role, because some of these glaciers look like they have tongues. Like the middle has really moved so fast that it looks like it's sticking out, which is kind of fun. There we go. So this is kind of what I was thinking about here. So it's got this like tongue that's moving down as the channel is slowing down the edges. Perfect. Okay, great. Thank you, everyone. So that was our first tool. It really also sets some key foundational information for your students that they are going to be referencing for the rest of the activities. So it is a nice one to start with. And we, from those activities, learned that ice flows and ice moves due to different forces. So now we're going to be using one of our first remote sensing tools, and it's Google Earth. So maybe some of you have used Google Earth in your classroom already or in the past. We're going to be using it to explore global glaciers. So now I'll do a quick simulation of how you're going to run this, but then we're going to use breakout rooms so you can work in teams to explore each one of these glaciers. So first, I'm going to open up Google Earth here. So it's really a great tool. You can type in anywhere in the world and it will fly you there. I'm going to start by exploring Pine Island Glacier, which is in Antarctica. So I'm going to type it in here. You just click enter, and no matter where you are in Google Earth, it's going to fly you to that one spot that you want to see. So it's flying me all the way to the bottom of the Earth. Great. So this is a little bit of info. Most of the time it's pulled from Wikipedia. I'm just going to X out of that for now. I'm going to zoom out a bit so you can see the full extent of the glacier and the width. So in the worksheet that Margie had put in the chat, you're going to notice that it's asking you a couple questions. It's first identifying what glacier you're looking at and what continent you're in. Then you're going to measure the mouth of where this glacier is depositing into the ocean. And the key thing about this is to show students that not all glaciers are the same, and that they all look different. They're all in different locations. They all have different topographies around them. And so you are going to use this measuring tool in Google Earth to go ahead and measure the mouth. And sometimes it can be a bit tricky to see where it is. So not every student who has the same glacier is going to get exactly the same measurement, but it should be around the same for each of them. So for me, I clicked on this measuring tool. We're using kilometers, but you can change it to whatever you would like in terms of units. And I would say the glacier's flowing from maybe about here. You just click once, you drag, and then you double click to end. So the reason why I chose these 2 points, looking at the mouth of where this glacier is depositing, is just because I can kind of see the glacier, evidence of glacier movement. And so I kind of clicked where that is. What you're looking for is something called the grounding line. So it's where the extent of the glacier is grounded to the bedrock of whatever landmass you're looking at. So for this, we're looking at about 41.5 kilometers. So seems like a pretty big mouth, but let's compare it to another glacier. So I'm going to, oh, and sorry, I also forgot to mention, the worksheet also has you exploring one observation about this glacier, one thing that surprises you, and then one question you still have. So every student group will fill that out, and then it's like a share and compare at the end. So I just wanted to mention that bit. But for this demonstration, we're going to now fly to Jakobshavn Glacier in Greenland. So we're going to the opposite pole. We're going to the North Pole now. Flying all the way up here. Okay, ooh, stop. So I'm going to zoom out a bit. And you can see, actually, I'm going to zoom in a bit. So this is kind of like a compilation of different satellite images that have kind of been mapped together. So Jakobshavn Glacier looks very different from Pine Island already just from this visual shot. What you can see is maybe some evidence of where the glacier used to have extended, but now you can zoom in and kind of see that this is all ice rubble called melange. And so what we're really looking for, again, is that grounding line. So where is the ice extent grounded to that bedrock? And so for me, you can see this ice stream here, right here. So I would say I want to be on top of it. The measurement that you would want to look at is maybe from there, so to there. So that's about, oops, I forgot to double click and end it. 13.67 kilometers. So in comparison to Pine Island, that is a much narrow mouth. So it just shows that all these glaciers are so different. So now that you kind of have a sense of how to use this tool, I'm gonna let you guys explore. We'll break you into different breakout rooms. I can do that now. Let's see. Margie, is there anything else that you wanted to add?
I don't think so. I think the goal of this is just for you all to get a chance to be comfortable. I put the questions that we are posing on the student worksheet so that when we come back and share, it would be nice if you could share with the people that are in the room. And there are 3 that we haven't explored yet that are in the worksheet. Actually, I forgot to put those names here. So one would be did you guys download the worksheet, or should I just keep doing this? I'm not sure where we are with people. Yes, no, sounds like maybe not. So Bruggen Glacier is one, Bering Glacier is another, and Tuna Breen, sorry, I can't type and talk at the same time, is the third. So we're going to put you into 3 groups and ask you to collect the information that's in these questions. So what's the name, what continent are you on, or where are you in the world? And then measuring the mouth or the area where it goes afloat, as Laura was just mentioning. And it is fairly visible if you're looking at, but you might have to kind of zoom out and then zoom back in to get that sense. It has a whole different texture when it's flowing over the land as to when it ultimately goes afloat and starts to break apart. And then one observation and one thing that surprises you in a question you have, and you guys could do that as a team, a little group, or you could do that individually, either way. And we thought maybe this would be like about 5 to 8 minutes, and then we'll pull everybody back and kind of hear back and then move into the next thing. Sound good?
Perfect.
Yeah.
So I have all the groups set up. I'll pull you guys at around 10:40, but if you have any questions, just feel free to ask. Okay, have fun.
Give it back.
Oh, great.
We're back to seeing the recording icon.
We're back to recording.
Good.
Awesome. Okay, welcome back, everyone. I hope that was fun, kind of getting to play with the tool. Margie was chatting yesterday, we just felt like being able to go right into the tool that you're going to be using in the classroom is so much easier to learn from than just watching a demonstration. So I hope you had fun. Okay, we're going to go through and just share a little bit about the glacier that you explored. So we can start with the Bering Glacier. What was the mouth size? What was something you observed? A question that you have, perhaps something surprised you.
That was us, right? Yeah, hold on a second. Okay, hey Laurel, that was a lot of fun. Really enjoyed it. Thanks for helping us use the measuring tool. So yeah, so it was interesting how that particular glacier emptied into the Alaskan Gulf. So this is right off of Alaska, and so making the measurement to see how it empties the ocean was definitely fascinating. I have to say, is Kathy here? I don't know if Kathy still has hers. Kathy, is yours still up?
Yeah, do you want me to share it?
Yeah, why don't you share it? Yeah, that way everybody can see what we're looking at.
Awesome, great idea.
Oh, there you go, perfect. Again, I'm going to be very honest again. I don't know anything about this stuff. So I already got the one question wrong where I thought the toothpick was going to fall back. So I'm a little bit confused by the center part. Like, Kathy, can you go in the middle part of it again? When you look at this glacier and how, that's good. Now if we get a little tighter, perfect right there. And I see how it kind of meanders, or kind of reminds me of a stream meandering. When I know how streams are, that they tend to meander more and make those S curves as it gets flatter and flatter. What I found interesting was that it looks like striations of muscle almost through the way it's just kind of flowing back and forth and twisting and turning. And I assume that's the way the ice does that. I'm just wondering why the center part looks so twisty and turny. Is that an indication that there's any water beneath there? Is that affecting the flow of the ice? That was just something that I was just wondering what that was, that pattern.
That's an awesome observation. Okay, so Margie, you can correct me if I'm wrong. My understanding is that this area is disrupting the flow of the glacier. So it's higher elevation. So the glacier right here in the middle, where you can see these like clear, straight-ish lines that are like, you can see the flow of the main channel of the glacier undisrupted, but then you have this higher area that's going to start to, just as you said, Sean, ice will flow the way that's easiest for itself, just like water is going to flow. It's going to flow the way it flows. So it's just responding to this higher elevation bit. Is that right, Margie?
Yeah, I'll just add actually that the thicker the ice is, the less of this you're going to see. So if you have really thick ice, it's just going to, by the time, it mounts, it's going to lose that connection to the base in terms of having that morphology. It'll just flatten out. But as it gets towards the edges, of course, it's thinning out. And so it is picking up some of the terrain that's underneath it. In addition, you probably are seeing a little bit of, you guys are probably used to thinking of moraines, or you've taught about moraines. So you're seeing, through time, it will have kind of pushed and shoved some sediments and materials. And so some of that is kind of poking up and visible through this. And moraines appear in, multiple areas around the ice, around glaciers.
That's perfect. I think your group was actually talking about moraines while you were kind of trying to figure out where the mouth should be measured. So you guys are right on point. Awesome. And so that was about like 15 or so kilometers wide in terms of the mouth. Perfect. Okay, let's move to the tuna breeding group.
That was us. So I can also share my screen.
Yes, extra points for this group because we took them through 3 glaciers before we let them land on one.
I'm sorry.
That's okay. It was great practice. So we had tuna brine. It is in the Scandinavian area, the Svalbard area. So this is where we were in the world. And then if I zoom in, so we found out that our glacier is actually 3 different glaciers. So we have one here, one coming in this way, and I guess one coming in here, correct?
Actually, they're like 1, 2, 3, just boom,
1,
boom,
2,
boom.
3.
So yeah,
Okay.
so you see the
Okay.
little one that's kind
Oh,
of
yeah.
swirling. Yep.
Okay, so it's 3 glaciers coming into one mouth area. So our measurement was just under 3 kilometers. One observation that we made was, to actually be able to visualize the drastic change between ice on land and all the texture that we were just talking about. And then the, I guess, smoothness of the ice that is already made it to the water. So we found out that all of this ice here is afloat, that, the land stops back in this area. So that's what we found out.
Awesome. Great job. And I'm so sorry that I had
That's
to.
okay. It was practice and it was awesome. Thank you.
That's a very positive outlook. And it's so interesting because your mouth, 2.95 kilometers, so much narrower than the first one that we looked at, and from Pine Island Glacier, which was massive and even smaller than Jakob 7. Okay, awesome. Let's move to our last one. So that is Bruggen.
Okay. I don't know that we have a screen to share.
I'll share the screen, Millie. You talk.
Okay.
You were the best.
Christiane, thank you. So we had Bruggen Glacier, which initially took us to Germany. But, of course, there are no more glaciers left in Germany. So this one is in Chile, in Patagonia. And I had to zoom out to kind of see that we were actually oriented facing south. And so it's this long area, which I think is probably like one of the biggest glaciers left outside of Antarctica, or at least in the Western Hemisphere. I don't know if there's any, probably Greenland is, but anyway, we measured that to be around 4.7, maybe almost 5 kilometers. And like I said, I think when we zoomed out a little bit, it was surprising to see how it's melting all around. So there was like a very wide stream or a series of streams. And we were just wondering whether we were in winter. Is this a winter view? Or is this summer melt out? That was one of the questions we had.
Oh, that's a great question. So there are glaciers on every continent except for Australia. And so all glaciers don't necessarily have to be tied to an ice sheet. They can be tied to like elevation. So it's like cold and there's snow at the top of this mountainous area in Chile. And so you can have glaciers form there. I don't know what season this was taken, but this glacier is not seasonally formed. It's like a long-term glacier. However, you are right in that there is changes in dynamism in glaciers from seasons. So that is, and ice in general has changes through seasons. And Margie is actually going to talk about that in a little bit.
Yeah, but I also wanted to mention, so this is in the Patagonia ice field. And so Patagonia is one of our, sometimes it's called the third ice sheet because it is one of the largest still remaining extents. So you did hit that right on the head, Millie, in terms of that it must be one of the largest in this area. And yeah, there still remains a fair amount of ice in that particular area, especially during the winter time.
And I didn't see the mouse size. I think it was about like 4 or so kilometers.
Yeah, it was under 5 kilometers, 4.7, I think you said, Christiana, right?
And 4.73, 4.8, that's what we got.
Yeah.
Yeah.
Okay, so that's also kind of relatively small in comparison to the others. So I just want to give you some glacially fast facts. Pine Island Glacier, so the first one that I showed from Antarctica, it doesn't look like it, but it is very steep. And it has this very wide mouth where this ice is depositing into the ocean. And I want to make sure we mention that ice that is shed from a glacier and enters the ocean, it's not a bad thing. There is this ice equilibrium where you have ice that is being deposited, but as long as there is an equal amount of snow that's being contributed to form more ice, then that glacier, that ice sheet, that system is in balance. It's challenging when you have a glacier that's depositing more ice and retreating faster than you have that snow that's being deposited. So that's important to know. But that being said, Pine Island Glacier, very steep, has this wide mouth. Seems like there's a lot of opportunity for that ice to flow into the ocean. And then we have the Jakobshavn Glacier right here, which is not as steep. And as we measured, it has a larger mouth than some of the other smaller ones like Bruggen or Tunabreen, but it is narrower in comparison to Pine Island Glacier. So that being said, and thinking about our glacier physics, which of the 5 glaciers that we explored do you think is flowing the fastest? And why do you think so? Maybe it's hard to tell from the evidence that we have so far.
Yeah, hard to tell.
Given the silence. Okay, that's totally fine. My personal initial reaction would be like, oh, it's got to be Pine Island because it's super wide. It has this very steep incline, so it's got to be moving fastest, right? Like it's got to be just flowing all of this ice and depositing into the ocean based on those characteristics and based on what we know from the Bergy Bits activities. But in fact, it's actually Jakobshavn. Jakobshavn is the fastest moving glacier in the world. And yeah, anyway, before I say too much, does anyone want to make a hypothesis on why? Why do you think Jakobshavn is so fast?
Is the terrain very smooth under the glacier and therefore there's less friction?
I also think it has to do with the amount of precipitation in Greenland, and gets a lot of precipitation, and it's got a narrow channel, so it's got to get all of that ice out quickly.
Oh, those are 2 great hypotheses. Does anyone else want to make a hypothesis?
Yeah, I'll make a hypothesis. I think of like a pipe, and as a pipe gets thinner and thinner and thinner, the pressure increases, the speed goes through. It's still the same volume, but it has to go through faster. So I think it has a lot to do with the landmass or bedrock around that's forming that channel. And if that channel is narrow compared to the large area behind it, it's just going to push it through faster.
Interesting. Okay, awesome. So in the classroom, you would have your students write down all their hypotheses, and you wouldn't like you would just continue on with the lesson to have them kind of explore their own answers, and then we're going to come back to this same hypothesis at the very end. Okay, so keep those in mind. Margie's going to continue on with that at the end. All right, and our third tool is Google Timelapse. So this is awesome. It allows you it's also created through remote sensing, and it allows you to observe changes anywhere in the world throughout time. So this tool can be applied to anything in your classroom, but of course, we're going to be focusing on the polar regions and specifically Jakobshavn. So let me try and move you all around. You can type in anything in the chat here. You can even use lat long if that is easier for you. But it starts at 1984 and it goes through 2020. So I'm just going to run through this a couple times and have you all observe the changes of this ice sheet.
I don't see it moving.
Yeah,
We
it's
can't see it,
not
Laurel.
moving.
You're not sharing your screen.
I'm not.
That screen.
Sorry.
No,
It's
that looks right.
Okay,
Okay.
awesome. So sorry, I was doing a little intro and I didn't even realize you can see it. So you can type in anything here and in lat long and go anywhere in the world. And this starts from 1984 to 2020. So I'm just gonna zoom in a smidge here so you can really take a look at what's happening with this glacier. All right, so I'm gonna also stop it on 1984. Oops. In comparison to 2020, so we can really see the start and end of this glacier. So this is 1984. This is 2020. What do you observe?
Melted.
Someone.
quite a bit of,
Sorry, go ahead.
So Ruben says it's moving faster and Millie says it's melting.
Yeah.
Yeah, so it is pretty clear from Google Earth that we have these glaciers that are flowing. And I told you that that's not a bad thing. There is this equilibrium that where these glaciers can be in balance, but this is showing us that this glacier is not in balance, that this glacier is actually retreating through time. And so that is not, that seems to suggest that humans are playing a role on impacting the system. And so you can even see here, this is that melange that we were talking about, where it's like all that ice rubble that's floating in the water. And so the ice sheet has been retreating back. Okay. This is an image. Can you guys see this?
Yes.
Okay, great. Just want to check. This is an image of Jakobshavn, and it looks at the retreat through time. So not only is this glacier retreating, but the retreat is accelerating. And the way we know that is because some of these melt time periods are narrow at the beginning, but as we go through time, the melt is more through shorter periods. You can see that retreat is accelerating, and it's even looking in shorter time periods through here. So that being said, I'm gonna pass it off to Margie now.
Okay, so we've looked at a couple of different tools. Now we're going to look at a whole different aspect of the ice sheet, and we're going to just focus a bit on the surface of the ice sheet and using our eyes to kind of see some of the changes that are going on. So this particular image, first I want to get you to focus on where we are. So where are we on the Greenland ice sheet? And we're going to do some touring around different locations. So I think it's really important for us to center our students and yourselves on exactly where we are in terms of what's going on and what are the changes we're seeing. So we're kind of down in the lower third of the southwest component of the Greenland ice sheet. We're actually about 80 kilometers in from the edge of the ice sheet. So we're just inland from where the ice sheet kind of starts. And I want you to kind of take a look at this. This is early summer in Greenland ice sheet. Any observations you want to make about it? You can just put them in the chat or say it out loud. Pretty white, right? So I think a lot of people, when they look at this is exactly what they think that it's going to be like to look down on the Greenland ice sheet, that it's a massive amount of white. There's not a whole lot of differentiation going on the ice sheet. If you focus in hard, you can kind of see two little kind of blue hatch marks on one on the right and one on the left of the ice sheet. So we're going to ask you to kind of keep your eyes on that, and we're going to pop it. And so you can see those little hatch marks develop through the course of the summer. So we just moved from the beginning to the end of the summer. And you'll see that the ice surface looks very different through that period of time. So the kind of thin connector lines that are on here, like the veins, I would call it, are surface meltwater channels. Then you have these little pockets or pools. Those are what's called supraglacial lakes. So lakes that sit on the surface of the ice sheet, or meltwater lakes, either one. They have many different names. And you can see that it's quite visible. There's a lot of water that's kind of sitting on the edge of the ice sheet. Okay, so in the worksheet, this is set up so that students can make a claim. They can state some evidence and they can do some reasoning. And one of the reasons that I wanted them to do that is I wanted them to come away with a claim that was bounded by the evidence they're looking at. So I would expect that a lot of students would say the ice sheet changes during the course of the summer using this bit of data. But really, we can't say that, can we? Because we're only looking at a small portion of the ice sheet. And as I've mentioned, and as we can see on here, we're looking at the southwest. So an area that is going to be closer to the mid-latitudes, so a little bit towards the warmer side of Greenland. So the goal here is to get them to kind of keep that claim restricted to what the evidence is that they're looking at. Okay, so this is beginning of summer, end of summer. Now we're going to move to 10 days of data. So we're looking at, this is the first image, it's July 21st, and we're not gonna go there yet, but the second image we're gonna look at is August 1st, so about 10 days. We have moved a little bit further north on the edge of the ice sheet, so you can see the little square has popped up on our map. So we're moving a little bit north. We could kind of form some opinions or make some hypotheses about what that might mean in terms of weather or temperature. And you can see Jakobshavn. So you can, and using your little toolbar, you could also see that we are, about 40 to 60 kilometers in on the edge of the ice sheet. So not too much different from where we were as we were further south. And we're going to look at two images. These ones are not going to be as strikingly different, so you're going to have to focus in on this. So there is a notation on here that says melt lake that you can take a look at. And now we're going to plop to the next one. And again, there's a notation that that little melt lake seems to have gone away. So drained, disappeared, which is interesting. I would expect our students would hypothesize that during the course of the summer, that melt lake might get bigger, that we might see more of that. We do see down here on the bottom, if Laurel goes back to the last slide, yep, and then we're going to go forward and you'll see that that lake does increase. And in addition, again, there's a place where they can make observations. They might point out that the ice sheet got a little bit darker during this period of time. It's not as white as it was previously. On both the left and on the right-hand side, there's a little bit more darker ice. This happened to be collected in 2019. It was a warm year, which meant there was not a lot of snow that fell that year. And because of that, the snow is that wonderful white color that sits on top of the ice. It's actually more reflective, has a higher albedo than when you have just ice on the surface. And so if you have less snow, it goes away more quickly, and then you have a darkening of the ice sheet that occurs. So now we can look at the fact that not just over a season and not just at the very southwest, but moving further north, we're seeing changes occurring and on a shorter time scale. So that could be the claim that they're making, that this time scale shortens. Okay. Now we're going to go to a little bit of a different way of looking at data. We're going to zoom in on a graph. So if we orient ourselves on the x-axis, we're looking through time. We're going from 1970, 71, all the way through to 2060. So clearly we haven't hit 2060 yet. So some of this is not actual collected data. Some of this is going to be modeled from data. So this is a combined graph that's looking at data and then modeling that data forward. On the Y graph, we have elevation. So surface elevation. And as a point of orientation, I want to point out that we put the Greenland ice thickness model. Remember the ice thickness map that we looked at earlier? It's sitting down here in the corner. So where would we expect to find thicker ice, higher elevation on the Greenland ice sheet?
In the center.
Center, yeah.
In the center, exactly right. So the edges of the ice are much thinner. And as you move towards the surface, it's almost domed. It gets to be thicker. So melt and changes that are happening on the edges are happening at a lower elevation than as you move into the interior of the ice sheet. So changes we would expect, a hypothesis here would be that we could expect that changes and melt might be occurring earlier or more often at lower elevations than as we move towards the interior. So now we're going to look at the data that was collected. And these black hatch marks are actually showing us data from the furthest interior, the furthest, highest elevation, sorry, that they noticed meltwater lakes, okay? So in 1971, you see this large line, that's all the lakes that they tallied. And you can see that the preponderance of them was between 1,500 and 1,625 meters above sea level. Then we go to, and that stayed fairly stable for a number of years. Then we go to about 1988, I would say, and we'll see that it's moved higher in elevation. So we're at 1625, perhaps to 1650 meters above sea level. And then that stayed stable for a while. And then we moved in towards the end of 1900. And you see at that point, it starts to change pretty regularly. Like every year, it seems that we're moving further and further up in elevation, which is also moving inland in terms of this, more of the ice sheet is seeing these surface melt lakes and surface meltwater channels. And in fact, the data showed that the spread of lakes went in by 53 kilometers between 1971 and 2012. So quite a move in. Then taking that data from Ian Howitt, a modeler, oops, go back. Sorry, we're not working very well together. Taking that data, a model was developed, and the model is, so the thin purple line is actually the model run. So you can see that it's kind of following along, and the thicker purple line is the trend line. So kind of taking that data and averaging it and showing the trend. And you can see that the trend is following with the data, which is not a big surprise. When they ran the model out, she came up with that in that same period of time that it went in 53 kilometers, she got 56 kilometers. So you can see that there's pretty good adjustment or pretty good correlation between the model and the actual data. And so you can see that if you looked at the modeling data, we're moving in almost to the middle or the interior of the ice sheet, which is only about 3,000 meters thick by 2060. So we would be seeing a lot more of the surface of the ice sheet with these meltwater ponds. And now I'm going to have you, sorry, Laurel, now I'll have you go to the model. So this is a visualization of that model so that you can see how it would actually move up the ice sheet through time. So by 2060, it's much, much further inland. Does this make sense?
Yes, yeah.
Mm.
Yeah, anybody have
Yes.
questions about this?
Mm.
Okay, so then, and if you do, please yell. Because this is a little bit different way of looking at it. We've been looking at these very visual images, and now we're trying to take that data and look at it in a form of data. But again, we can make a claim about this, and we can look at areas of the ice sheet that are really being impacted and how this is moving towards the interior. So it's not just being restricted to those perimeter areas, the 80 to 100 kilometers from the edge of the ice sheet. We're really moving further in from that. Okay, we're going to go to the next set of images. So this is a series of 3 images. These are taken almost exactly a month apart, June 3rd, July 4th, and August 17th. So 6 weeks there instead of a month, in the year 2010. And what we want to look at, now again, orient yourself on the ice sheet. So we are pretty close to Jakobshavn still. So kind of in that, just hitting the middle part of the ice sheet. And we're going to look at a series of 3 images. I want you to focus on the top right of the image right now, and you'll see that that's a surface ice stream. So that's like a meltwater channel that's moving down across the ice. And I always say, if you look at the Greenland ice sheet from above, it kind of looks like a string of pearls. It has these meltwater channels, and it has a little lake and the meltwater channel. It kind of collects in a little area, and it's beautifully kind of strung across the ice sheet. I also want you to look at the toolbar, and you'll see that it's 500 meters, so that you can kind of get a sense of the scale of some of these meltwater ponds. And we're going to, so this is June. We're going to move to July, so a month later. So
Oh my
significant,
God.
yeah, significant difference.
Mhm.
And now we're going to go to August.
Mm.
Oh, so what do you think happened there?
Mm.
It drained down to the bottom of the glacier and maybe formed some meltwater along the base.
Exactly. So what we can see here is, and this might not be intuitive, because the expectation, again, kind of going back to that earlier 2 sets of images that we looked at from June to August over a 10-day period, it might seem that we would get bigger and bigger and, you know, become a massive lake on top of the ice. But in fact, as you get enough water pooled, it will kind of force, it's heavy, it forces its way into a weakness in the ice sheet, and it forms these channels, which are called moulins, and they'll just drain that water down from the surface down all the way to the bed. And in a matter of minutes to an hour, they can do what wouldn't happen in that period. You know, it could take 10,000 years for that ice to go away and us to have water down at the bed. So these things really change the timing by just opening up pockets. And Laurel's gonna show us a little movie that'll kind of bring this up close and personal.
He threw it straight into it. He didn't even give it a little float time.
Oh, much better.
Roll the dice, feel the fear in my enemy's eyes. Listen as the crowd would sing. Now the old king is dead, long live the king. 1 minute I held the
Second year, this is dry. So we should try.
Really see how deep those are.
That lake, so we should try to get one
into that hole. Yeah.
To let me in, shattered windows and the sound of drums. People couldn't believe what I've become. Revolutionaries wait for my head on a silver plate, just a puppet on a lonely string. Or who would ever wanna be king? I hear Jerusalem.
So nobody ever said scientists don't know how to have fun. And I also wanted to mention that when you're working around moulins and those meltwater channels, the water's moving pretty quickly and they do tether you. So it's not as if they're just out there looking down a hole and, you know, hoping for the best. There's a lot of safety precautions which don't show up in some of these because they're kind of behind. But just to point out that this is all done with safe material. Okay.
I was happy to see the tethering, I'll tell you.
Yeah, it's really important. So, and NSF is very aware of that. I think that was actually a NASA funded project, but they also were very careful about that. So I want to kind of pull all this together in this image, and here you'll see there are meltwater channels, there are surface lakes, and then you'll see this moulin and how it actually drains down to the base of the ice sheet. And I wanted to pose a question here for you guys to think about, and I want you to put your thoughts in the chat if you would. So which of these do you think might be the most important in terms of creating change that's going on in the Greenland ice sheet? Do you think it's the surface meltwater channels? Do you think it's those lakes? Do you think it's those moulins? Or is there another hypothesis that you could come up with? What do you think is the most important part? And this is all part of what we call either glacial hydrology or glacial plumbing, depending on who you are, but like, how is all this working together?
The water that collects from the moulin, does that speed up the flow of the ice above it?
Above it or below it?
Well, above it, because now the ice isn't in contact with the bedrock for friction. It's sliding on the water below
Oh,
it.
the whole, I'm sorry. I thought you meant surface versus
No,
base.
I mean at the
Oh,
bottom.
we're gonna talk about that. Don't jump the gun.
Sorry.
No, don't be sorry. I'm kidding.
So Marianne says moulins, Christy moulins, Mike, crevasse formation, Kathy moulin due to moving the water to the base of the glacier.
So crevasse formation, we didn't talk about, but sort of indirectly we did. So as you get this meltwater collecting in lakes, it finds weaknesses in the ice, and those tend to be little braced crevasses, so little areas that open, and then they force open with the weight of that water. So they're kind of, yes, they form without the water being present at all, but then they get really energized, I guess is a good way of saying it, by the water that forms. So moulins clearly play a critical important role. I would say actually it's all of them together. So surface meltwater is huge. Those meltwater channels, I know that the gentleman who was studying and collected some of the earlier images that we looked at, his study looked at 550 of these surface meltwater channels. All of them ended in lakes and all of them ended in moulins. So it's really all part of a cycle, a system that works together. And you're absolutely right, Jen. So anything that's darker that's sitting on the surface of the ice sheet is going to be absorbing more heat, right? So it's going to have a lower albedo and it will just be pulling heat in rather than reflecting it. So the lakes are huge in terms of, that's why they continue to get white. It's a feedback. So it's that all part of a positive feedback. So as it sits here, more energy is absorbed, it's melting more ice around it, and they just get larger and larger. And then that really takes that water down. And so to answer your question, Jim, yes, as that water gets down to the base of the ice sheet, it will then cause, I'm waiting for Laurel to click. I'm sorry. There it is. It lubricates the bed, and Yeah, and you'll remember Laurel talking about basal friction when we were looking at that glacier goo. So that brings it all back to this. So you kind of lubricate and you remove some of that friction and really cause it all to kind of move more readily forward. It's kind of a, did I answer your question, Jen? I think so.
Yes, thank you.
Okay, yes, that's that whole albedo component. Okay, so we're going to thinking about all of this. So we've looked at a whole bunch of different processes that work together. Now we're going to go back to your hypothesis that you formed earlier and what was making Jakobshavn the fastest moving glacier in the world. And I wondered if anybody wanted to amend their hypothesis, or are there more things that we could say about it, having done a little bit more of an exploration of the hydrology that's going on. What do you guys think?
Well, I'll jump in with probably has more lubricating water beneath the glacier, and that's why it's moving faster than the others.
Yeah. Yeah. So it is a well-connected glacier. There are a lot of, so first of all, it's not just a simple anything. So again, all of these are a system and there are multiple factors that play in, but a huge one is what you mentioned and what Sean says, that there is, now that you have all this water that's getting down to the base, it's really lubricating and causing it to flow more quickly. And Jakobshavn happens to just be at an area where it drains a large part of the ice sheet. It is wet. It's a wet based glacier, which is happening around Greenland a lot now because of the way that it's warmer in the northern hemisphere by just that much that it's causing melt on the surface. So we don't see as much melt on the surface of the Antarctic ice sheet as we do the Greenland ice sheet. And so that's putting that wet base underneath the ice and allowing it to slide versus the ice being still stuck fast to the base of the ice, to the base of the bed. Okay, and we're going to go to our next slide. Great. So we've kind of dug into a whole bunch of essential questions. We've looked at what's driving change in these icy areas. So it's a combination of a variety of things, but it's a full system of feedbacks, and water is a critical part of it. We collected a whole lot of evidence. I think if you were doing this with your students, you could go back and look at all the evidence that they collected through the course of their investigations to really see the changes that are going on. In terms of how quickly these polar regions are responding to change, they, certainly if we went back in time and Laurel took us through that wonderful step through with the Jakobshavn Glacier, and you saw that there was some pretty good stability until it really starts to accelerate as we get closer to present. I also showed you that graph that showed the surface meltwater ponds and how those stayed relatively stable in terms of where they were showing up on the elevation of the ice sheet for a number of years, and then suddenly has really accelerated. So from 70 to like the middle of 80s, it barely changed. And then suddenly by the time we got into the 20s, it was really moving. And then we looked at even shorter time scales. So we looked at things that occurred over a season, things that occurred over 10 days, over a month. So we really see these changes happening rapidly. And then of course, moulins, which can happen over the course of an hour. So really a dramatic timing differences. Certain processes enhancing ice loss and ice flow. Yes, I think we saw that the moulins and just the amount of water that's on the surface of the ice sheet is really having an enhanced ice impact. How can we monitor Earth's changes? So we looked at a variety of different satellite tools. We focused heavily on satellites today, which was the goal of this experience, and hopefully you enjoyed some of those opportunities. And then how are humans part of Earth's system? So we didn't dig hugely into our role in terms of climate change, but I never like to have a conversation or a focus on what's changing without realizing that we're all part of the system, so that we have a connection into it. And with that, I think we're ready to do questions.
Okay, I have one. If the Earth is warming, there should be more evaporation off the oceans, or more evaporation taking place. But also, the precipitation that would follow from a warming Earth wouldn't be in the form of snow, it would be in the form of rain or water, liquid water, which would exacerbate the sliding of the glaciers, because now instead of the glacier being replaced with snow, it's being replaced with water falling on it. Right or wrong, or
no,
combination of both?
No, you're right. So actually, Greenland and Antarctica have been seeing more rain than they've seen in the past. In fact, last summer, they had rain at Summit. Summit is the very interior of the ice sheet. That had not happened in our recorded history of, recording measurements at Summit. So yeah, it's definitely changing. I think that there's been a lot of modeling and research that's gone on that says perhaps at a certain point there'll be a tipping point. There's always a tipping point, right? Where that the changes in meltwater runoff will change circulation patterns, and at a certain point it might then slow things down, stop, cool it a bit, and then we would have a change to that precipitation and things would slow again. We don't, I guess there's a lot we don't know. There's a lot of modeling and research going on, but you're absolutely right. There is definitely, we see the increased rain that's happening in Alaska as well, even though Alaska's been having a lot more problems with dry, but less snow, more rain.
Yeah.
Any other questions?
Giving people a chance to think of some. Just want to invite everybody to come back in 2 weeks when we're going to have a talk which will expand on this. And Chris Sapp is going to talk about using drones to monitor polar regions.
That'd be fun.
Is that on the 19th, Mike?
That's on the 19th.
Well, if the cruise ship has an internet, I can join you. I'll be out at sea. We're making our way down to Cozumel.
Well, we wouldn't want to stand in the way of that.
Well, the ship has internet, but I have no idea if I can get. I'll do my best.
Catch the recording.
I'll do my best. I'll have my laptop with me.
Okay.
Well, thank you guys so much. It was great having you all, and I know Saturdays are precious, so we really appreciate your giving up some time with us.
Thanks to both of you.
Thanks.
Yeah.
And just a reminder, we will be sharing the teacher packet, the worksheet, the answer sheet, some of the videos, anything that you would like, so you can actually plug this into your classroom. And then if you do, we would love to hear how it goes.
Yeah.
I'm sorry, one question, Margie and Laurel. There was one tool that you used, I think, Laurel, earlier. It wasn't exactly in Google Earth. I don't know if it was an extension or a tool where you showed how fast, right? Yeah, how fast, that's the one right there, Google Earth Engine. What is that?
This is Google Timelapse. So yes, I guess the URL is earthengine.google.com, but if you Google Timelapse, then that should come up too. And yeah, this is awesome. You can look at places all over the world, and then it even offers some time lapses that they suggest you can explore as well. So it's kind of fun.
Okay, great, thanks. That's very helpful. And my students are going to wonder what happened to the little duckies.
And you know what? First of all, we should warn you that when we share this, we aren't allowed to share it with that song on it. So we have that full thing with the song. It was used at an outreach event many years back. And so when you get access to it, it'll be without the music. It'll be the full video. So you'll watch that scared little ducky that was, they were actually doing it as kind of a hoax, as well as just wanting to see if any of those duckies showed up anywhere. They're still down there being ground around by the ice. At some point, they're going to spew out into the Arctic Ocean, and we're going to all be excited.
Future
up their life for
paleontologists are gonna
science.
Be very upset.
Yeah, I'm sure the plastic gyres are not going to like it, but
No.
anyway.
Well, we'll see if they end up in Cozumel. We'll have to.
Hey. I'll look along the beach. I do plan to hit the Mayan ruins. I'll see if there's any ducks washing ashore before I go in.
John, I was actually thinking about you in this particular experience because I know you love using your smartboard so much. I was thinking you were going to love like being able to navigate these kids all over the place. So
it's very cool, and when you do put it on something really large, you know, it becomes even more effective. So yeah,
absolutely.
Yeah.
Cool.
Thank
Okay,
you.
so
It
let
was
me thank
really,
again
really great
Margie
lesson.
and Laurel and Chris for recording. We'll send a message out when we have this posted.
Sounds good. Thanks, guys.
Thank you.
Saturday.
Thanks much.
Walk
Bye.
safely,
Take
everybody.
care.
Take care.
Bye.
Bye-bye.
Thank
Bye.
you.
yeah, nicely done. Thanks for the
Thank
invite.
you.
Thank you.
Bye.